Welcome to The Explainer. Today, we're diving deep into one of the most important devices you'll ever study in physics, the electric motor. Ready? Let's get started.
It all boils down to this one question, right? How does electricity actually make things spin? I mean, this is the magic behind everything from your phone buzzing to electric cars moving. And by the end of this, you're not just going to know the answer, you'll be able to nail it on your exams. I promise.
Okay, part one, from force to first turn. Before we can get anything to spin continuously, we have to understand the fundamental push that starts it all.
All right, listen up, because this is the rule. Seriously, a current-carrying conductor in a magnetic field experiences a force. That's it. That's the whole game. Everything, and I mean everything we're about to talk about, comes right back to this one single idea. So burn it into your brain.
So let's build our motor from the ground up, okay? First, you take a rectangular loop of wire. Let's call it ABCD. Now, we're going to place that loop right inside a nice uniform magnetic field, stretching from a north pole to a south pole. Then we just need to get some current flowing through our wire loop. Now, here's the really crucial part. See how the sides AB and CD are perfectly perpendicular to those magnetic field lines? That setup, that's exactly what we need to get things moving.
So, what happens now? Well, because we have current in a magnetic field, a force appears. On side AB, that force pushes the wire inward, and on the other side, CD, the force pushes outward. Now here's the thing. These two forces are perfectly equal in strength, but they're pushing in opposite directions. So what does that mean for the total force on the coil? You got it. The net force is actually zero.
Wait a second. If the net force is zero, how on earth does this thing even start to rotate? I mean, shouldn't it just stay put? If you push and pull on something with the same strength, it doesn't move, right? So what's going on here?
The answer, my friends, is a beautiful little concept called torque. Torque is just the turning effect of a force. Think about opening a bottle. You're not just pushing on one side, right? Use your thumb and your finger to create two equal and opposite forces. The cap doesn't fly across the room, it turns. That's torque. And it's the same exact thing with our motor. The inward and outward forces aren't on the same line, so instead of canceling out, they create a twist, a torque, that kicks off the rotation.
All right, part two, the half rotation problem. So our coil is spinning. Awesome, right?
Well, not so fast. Our simple little design is about to hit a major wall. After just one half turn, the very physics that got it started is about to bring it to a grinding halt.
Yep, the coil makes that first beautiful half turn, but then we've got a problem, a big one. The physics is about to betray us.
Let's trace what happens. At the very beginning, when it's flat, the torque is at its absolute maximum, and the coil accelerates. But as it rotates 90 degrees and stands up straight, the forces are just trying to pull it apart, so the torque drops to zero. But inertia. Once something's moving, it wants to keep moving. So inertia carries it right past that vertical point. But now, it's gone 180 degrees. Side AB is now where CD was. And this is the problem. The forces reverse their direction. The push that made it go clockwise is now pushing it counterclockwise. So the coil just gets shoved back and ends up, just wobbling back and forth. No continuous spin at all.
Okay, part three, the continuous spin solution. This right here is where the real genius of the electric motor comes in. How do you solve a problem where the forces keep fighting you? So the question becomes, how can we outsmart the physics? Is there a way we can trick the forces so they always push the coil in the same rotational direction? How do we hack the system?
And the answer, the hero of our entire story, is this little gadget, the split-ring commutator.
Okay, so how does this hero actually work? It's brilliant. Check it out. The two ends of our coil, they're attached to two separate C-shaped copper rings, C1 and C2. Together, they make up the split-ring commutator, and it spins right along with the coil. Now you have two stationary carbon brushes, B1 and B2, that are just lightly touching these rings, feeding them current from the battery. Okay, for the first half of the spin, B1 touches C1, and B2 touches C2. Simple enough. But here's the magic trick. Right as the coil passes that vertical 180-degree point, the brushes slide over the gap and switch contacts. B1 is now touching C2, and B2 is touching C1. What does that do? It reverses the direction of the current inside the coil at the perfect instant. And by reversing the current just as the forces were about to reverse, we keep the push going in the same direction. It's an automatic, perfectly timed switch that gives us smooth, continuous rotation. Absolutely genius.
And that, right there, is the whole purpose of a motor.
We put electrical energy in, and we get mechanical energy, that continuous spinning motion, out. So remember this for your exams. An electric motor is fundamentally an energy converter.
All right, part 4, mastering Fleming's left hand. So now we know why the motor works. Let's get our hands on a tool that lets you predict exactly which way it's going to spin. This is a must-know for your exams.
This is your secret weapon for any motor-related question. It's called Fleming's left-hand rule. And trust me, it's going to make solving these problems so much easier.
Okay, let's break it down. Take your left hand. I'm serious, do it with me. Stretch out your thumb, your forefinger, and your middle finger so they're all at 90-degree angles to each other, kind of like a little 3D axis. Now your forefinger points in the direction of the magnetic field. Your middle finger points in the direction of the current, and your thumb will then magically point in the direction of the thrust, or the force. A really easy way to remember this is FBI, force for thumb, B field for magnetism, forefinger, and I for current, middle finger. FBI. Got it? Now, what you see here is the official board exam perfect definition. You'll want to memorize this word for word. Stretch the thumb, forefinger, and middle finger of your left hand so they are mutually perpendicular. If the forefinger points in the direction of the magnetic field and the middle finger in the direction of the current, then the thumb will point in the direction of motion or the force acting on the conductor. Write that down, practice saying it, that's a full marks answer right there.
And just one last thing, so you don't get mixed up. People often confuse motors and generators. They're basically opposites. A motor takes in electricity to create motion. A generator does the reverse. It takes motion to create electricity. They're two sides of the very same coin. So just keep that distinction clear in your head.
Okay, let's do a super quick recap. What do you absolutely need to know? Number 1, a motor works because of the force on a current in a magnetic field. That's what creates the torque. Number 2, the split-ring commutator is the secret ingredient for continuous rotation. Number 3, its whole job is to flip the current's direction every half turn. And number 4, your go-to tool for finding the direction of the force is Fleming's left-hand rule. That's it, that's the core of it.
And we end exactly where we started. It all comes down to this one foundational principle. An electric motor works on the principle that a current-carrying conductor placed in a magnetic field experiences a force. If you truly get that one sentence, you get the electric motor. It's the beautifully simple physics of spin that, well, powers just about everything in our world.